Welcome back to Simplifying Synthesis. In this video, we are going to look at the total synthesis of ent-Trachylobane natural products. This work was published in Angewandte Chemie and was carried out by the group of Thomas Magauer. The ent-Tracylobanes are a large family of natural products, and the earliest isolation came in 1965 by Robinson et al., who isolated these compounds from Trachylobium verrucosum. Members of this family have shown anti-cancer, antifungal, and antibacterial activity, and they have attracted a lot of attention from the synthesis community due to their unique cyclic frameworks. This framework includes a distinctive cyclooctane subunit, comprising of 6, 5, and 3-membered rings fused together. In addition, there are 8 stereocenters and multiple sites which can be oxidized to form these natural products. It is the oxidation of these sites which is the main focus of this research. The retrosynthesis begins with these late-stage oxidations, in addition to other CH functionalization chemistry. All of the Trachylobane natural products synthesized in this work can be derived from a common intermediate bearing the polycyclic subunit. This moiety can be generated using an intramolecular Diels-Alder Cycloaddition, and the diene required for this reaction can be generated by the dehydration of an enone. The other alkene group required for this reaction could be installed using simple alkylation chemistry, and the tricyclic compound required for this reaction could be synthesized using a Robinson Annulation of a bicyclic compound, which the group had previously developed for a different synthesis. The researchers used a 2-phase approach for the synthesis: an initial cyclase phase, which is focused on constructing the carbon framework, and then a second oxidase phase, which utilizes CH functionalization to oxidize different parts of the molecule and generate different Trachylobane natural products. This cyclase phase starts off with a hydrogenation reaction to reduce the alkene present in their previously reported starting material. This then underwent a formylation reaction using sodium hydride, which forms an enolate which adds to methyl formate to form the dicarbonyl upon the elimination of methoxide. This formal group was added to the molecule to allow for the Robinson annulation to occur under milder conditions and improve the stereoselectivity of the reaction. This formulated molecule was taken forward without purification. It was reacted with triethylamine to form an enolate, which undergoes a conjugate addition to methylvinyl ketone. This addition product again forms an enolate, which undergoes an intramolecular attack on the cyclohexanone moiety, producing an Aldol Addition product, which undergoes an E1CB elimination to eliminate the hydroxyl group and form the enone. This enone then underwent a deformylation. The methoxide base acts as a nucleophile and attacks the aldehyde, forming a tetrahedral intermediate. This eliminates methyl formate and produces a conjugated anion, which is protonated to form the Robinson annulation product in a 41% yield over 2 steps. This deformylation reaction is favoured due to the stabilizing effects of conjugation with the enone. This makes the cyclization product a good leaving group and allows for the breaking of the carbon-carbon bond, as opposed to the more typical elimination of the methoxide group. It was important to use a methoxide base for this reaction, as the ester group already present in the molecule could undergo a transesterification if a different base was used. With this ring now formed, the researchers set about functionalizing the alpha position. An enolate was first formed using lithium HMDS, and this added to methyl iodide to form the product as a single isomer in an 81% yield. This stereochemistry can be rationalized by looking at the conformation of the intermediate, which has a hydrogen in an axial position at the beta position, which causes steric repulsion. A similar reaction was carried out in the next step, where an enolate was once again formed, this time using a mixture of LDA and TMEDA, and the enolate added to acetaldehyde to form the product in a 99% yield. This reaction had the same stereochemical outcome as the previous enolate addition, with the new group adding to the less hindered bottom face of the molecule. To convert this newly produced alcohol into the required alkene, the researchers used Martin's sulfurane. This first deprotonates the alcohol, and the resulting anion attacks the sulfur atom, together with the elimination of hexafluorophenyl propanol. A further protonation occurs, and another equivalent of hexafluorophenyl propanol is eliminated. This produces a diphenylsulfonium intermediate, and this can act as a leaving group, allowing for the deprotonation of the terminal carbon atom to produce the target alkene. With one of the three alkenes necessary for the Diels-Alder reaction now in place, the authors needed to reduce the carbonyl of the enone in preparation for the installation of the other two carbon-carbon bonds required for the cycloaddition. To carry out this transformation, they used a Luche reduction. Reaction of sodium borohydride with cesium trichloride in methanol produces the reducing agent. The carbonyl is activated by coordination to the cesium trichloride, which makes it more reactive and improves the selectivity for reduction of the carbon-oxygen bond over the carbon-carbon bond. The borohydride reagent adds a hydride to this carbonyl, producing the alcohol in a 76% yield. With this reduction complete, the stage was now set to carry out a dehydration reaction. This was carried out using the Burgess reagent, which was attacked by the hydroxyl group to form the activated species. The amide could then abstract a proton to carry out a 1,4 elimination. This produced the diene in a 46% yield. The researchers screened many reagents for this reaction, and they found that this was the only method that could produce the product in a way that could be purified, as the other methods produced byproducts that couldn't be separated from the intended product. This triene was then taken forward to the crucial Diels-Alder Cycloaddition. Heating the compound in a sealed tube at 175 degrees for 9 hours was successful in carrying out the cycloaddition, producing the product in an 85% yield. This is the first of the Trachylobane natural products synthesized in this work, and the characterization data was in agreement with that reported for the naturally isolated material. From this intermediate, the authors could synthesize a number of other compounds. The next reaction they carried out was a demethylation using sodium ethanthiolate. This acts as a nucleophile towards the methyl ester to produce the carboxylic acid upon workup. This product isn't observed in nature, but will be used in later oxidation studies. From this same methyl ester intermediate, the authors also carried out a hydrogen atom transfer using Shenvi's protocol. We saw a similar reaction in the recent synthesis of hamigerin M. This reaction used a manganese dipivyloyl methane complex, together with the silane donor and terp-butyl peroxide. This transfers a hydrogen radical to the alkene, which forms a radical pair intermediate with the manganese complex. Further transfer of another hydrogen radical produced the compound in a 99% yield, which again was in agreement with the characterization data reported for the naturally isolated material. Demethylation of this compound, again using sodium ethanthiolate, produced the carboxylic acid, which is another Trachylobane natural product observed in nature. The structure of this compound was proven by X-ray crystallography. Using this same methyl ester intermediate, they carried out a reduction, this time using red al, which is an aluminium hydride reducing agent. This adds a hydride to the methyl ester and forms an intermediate with the aluminium coordinating to the oxygen group. Further reduction and workup produced the primary alcohol in a 98% yield, completing the synthesis of yet another naturally occurring product. This alcohol was taken forward into an Appel reaction. The reaction of triphenylphosphine with iodine produces a phosphonium iodide. This is attacked by the alcohol, forming a phosphonium intermediate. The iodide then attacks the carbon, breaking the carbon-oxygen bond and eliminating triphenylphosphine oxide to produce the iodide in a 49% yield. The hydrogenation of this compound, using hydrogen gas, palladium on charcoal, and sodium acetate, completed the synthesis of compound 5 in a 94% yield. The completion of this compound brings us to the end of the cyclase phase of this synthesis. In the next video, I will look at the oxidase phase and detail the studies carried out to perform selective and non-selective oxidations of this interesting framework. Make sure you subscribe and hit the notification bell to be alerted when this video goes live. And as always, if you have anything you'd like to see, let me know in the comments down below.